what you would end up with then, the substantial derivative following that would be 0. And this then would imply that that term goes away. And we could divide through by the density because it's non-zero. And my continuity equation would reduce to just simply del dot V is equal to 0. Or in other words, if we expand that out and write it in detail, it would be partial u, partial x, plus partial v, partial y, plus partial w, partial z is equal to 0. Okay, so that has a particular physical meaning associated with it, which we're going to discuss next. But this is the more common form of the continuity equation. But if you write this down and call it the continuity equation, you better put a little asterisk next to it and say, for an incompressible substance. Because this is generally not the continuity equation for an arbitrary flow or fluid. Okay. So let's discuss about the ramifications of that. Just 2 more slides here. First, what does it mean to be incompressible? This is our continuity equation. Like we discussed, this is the rate of change. This first term is the rate of change of density as we follow a fluid element through the flow. So for example, let's say we mark this little fluid element that's shown there in light blue. And as it's going on, maybe it's getting heated up. And so its density would be expected to decrease, right? It would get less dense as I heat it up, if it's a gas. So if that term, this first term, is, if it's getting less dense, was that positive or negative? Negative. It should be decreasing, right? So that should be a negative term. In which case, what does that imply about the rest of this? It would have to be positive to balance it out, right? So the 2 positive and negatives have the same magnitude, and you end up with 0. So this really represents the rate of change of volume following the fluid element. So if that density were to be decreasing, then that volume should be increasing as it's expanding. Okay? So the corresponding volume must also vary in sympathy with the variation of the density. Now, if the density is constant, rho is equal to constant, then the density cannot be changed. And that implies then that the fluid element cannot be compressed. It doesn't expand, it doesn't contract, but the volume of that fluid element remains the same. So it would keep the same volume as it goes on, regardless of how it might get distorted or sheared or transformed. Okay, just to finish up and bring that home, let me give you a little thought experiment here for a simple arbitrary 2-dimensional flow. So del dot V in general is equal to partial u with respect to x plus partial v with respect to y plus partial w with respect to z. And if it's incompressible, then that's got a sum has to be equal to 0. If the flow is 2-dimensional, then we'd say that w is equal to 0. There's no out-of-plane variation here. And that third term would drop away, and it would reduce to just this form here. Partial u, partial x, plus partial v, partial y. Now, let's say du dx is positive. What does that mean physically if du dx is positive? The material following a fluid material element would have to accelerate. Let's say about the velocity field. What can you tell me about the velocity field? If I put a velocity vector on the left-hand side of the box in the u direction, and I go and put one on the right-hand side of the box, how would it be changed if du dx is positive? It would have to be bigger, right? It's going to be having a greater length. All right, so if du dx is positive, looking at our continuity equation for an incompressible substance, then that implies that dv dy has to be negative. Or that means v has to be decreasing as I go in the positive y direction. So here, if I take a reference velocity here, let's say it's pointing to the right, du dx is positive, that's going even faster to the right. Then if I have a v here, then this v is going to get smaller, right? For that to hold through. All right, so what happens if we let this thing move now with those velocities at those different boundaries? Well, the left-hand side moves slower than the right, and the bottom moves faster than the top. Those are going to get stretched out horizontally and compressed vertically as it moves. So it's changing its shape, but it's doing it in such a way that as I pull on it in one direction, it gets squeezed in the other to keep its volume the same. So this equation there in the upper right is nothing more than saying we're going to force our volume elements to remain the same following any sort of marked fluid element I could come up with. And that's a statement of the conservation of fluid volume for an incompressible substance. And this is sort of a physical picture that I'd like you to keep in your mind every time you write this equation. Any questions? All right, thanks for your attention. I'll see you on Wednesday.